Welcome. So we're going to be looking at some features of rational functions. A lot of these will be dealing with finding vertical and horizontal asymptotes. And we've only looked at very simple ones. We're going to learn how to find the asymptotes and holes for some other functions. It's really not that difficult to find holes. As matter of fact, it's not that hard to graph the equations with holes. I just tend to I go over the ones with just the asymptotes first, right? Because then you only have one thing to deal with, not an asymptote and a hole at the same time. So, but that's okay. It's not that difficult to learn where the hole will be. All right, so anytime you have something quadratic in your rational function, whether you're solving or graphing, go ahead and factor it if possible. 1 times 3 is 3. We need two numbers that multiply to give us 3, but add to give us the b term of 4. Well, that would be 3 and 1. 3 doesn't have any other factors. Right? So that would be x squared plus 3x plus x plus 3. And the first two are a group and the second two are a group. We could factor out an x. We'll have an x plus 3. We can factor out a 1, because they'd have nothing in common, and we would have an x plus 3. Right? We can factor out that repeating x plus 3, and we're left with x plus 1. So now if we rewrite this equation, f of x equals x plus 3 divided by x plus 3 times x plus 1. Oh, look at that. The x plus 3's cancel. And I had said that any factor in the denominator that doesn't cancel is a vertical asymptote. What about the ones that cancel? So our new function is this. 1 over x plus 1. Right? There's a vertical asymptote at the factor that didn't cancel. So x plus 1 equals 0, x equals negative 1. Right? So a vertical asymptote for the factor that doesn't cancel. The one that does is a hole. All right, so we have a hole at x plus 3 equals 0. All right, so add 3 to both sides, subtract 3 from both sides, x is negative 3. So there's a hole at x equals negative 3. So for the factor that cancels, so the one that does cancel, that is a vertical asymptote. For the one that, for the factor that doesn't cancel, it's a vertical asymptote. For the factor that cancels, it's a hole. All right? So we have a hole at x equals negative 3. So a vertical asymptote, actually I'll write it up here. A vertical asymptote at x equals negative 1, right? And a hole at x equals negative 3. I keep checking, make sure I have the right signs there. Now, if you were asked to find the y-coordinate of the hole, you would just plug it into the reduced function. Right? So I'll just put it over here. To find y-coordinate of the hole. I don't think you have to for the benchmark, but you will for me later, so I may as well show you. To find y-coordinate of the hole, it would be f of negative 3 equals 1 over negative 3 plus 1. And so that's just going to be negative 1/2. So there's a hole specifically at negative 3, negative 1/2. Right? That's where the hole is located. But I think it just asks you to find which x value there's a hole. So remember, if the any factor in the denominator that does not cancel, I should probably put for the factor in the denominator, let me just be really specific here. in the denominator. Because you can't plug in that value, right? It makes the denominator 0. That does not cancel. But when it cancels, it looks like, hey, what's wrong with -3? Right? You get a point and everything, and it's not undefined. However, it's undefined in the original. So because it's undefined in the original, you can't use it at all. Right? So here's our new function, but x still cannot equal -3. Right? Because it was a problem before. So for the factor in the denominator, I'm going to be specific because I'm going to post these as notes. There we go. All right, let's look at the next one. And by the way, if you want to read through these will get posted. All right, so you can read through those. And if you have questions, let me know. Select the equation represented by the graph below. All right, don't get too flustered. Just look at your intercepts, or let's look at your asymptotes. All right, so there's a vertical asymptote. Now this isn't the best graph, but I'm going to assume it's integer values. This right here is the y-axis. The lines go up by 5. I'd assume that this is x equals 4. Especially because these are all integers as asymptotes. The denominators, if you set them equal to 0, they'd all be integer values. All right, now the horizontal asymptote, again, each of those lines is 5. Looks like -2. Right? So x equals 4 is the vertical asymptote. Y equals -2 is the horizontal asymptote. All right, now let's eliminate some of our choices. All right, well here, the vertical asymptote is x plus 4 equals 0, x equals -4. Well, that's not right. That's on the positive side. So that's not that one. Here, it's also x equals -4 for the vertical asymptote. Go ahead and eliminate that one. Here, x plus 2 equals 0, x equals -2. All right? That's got the wrong vertical asymptote. Eliminate this one. Vertical asymptote, x minus 4 equals 0, x equals 4. Now, we're just learning this upcoming. The horizontal asymptote, these have the same degree. Right? We've learned that the horizontal asymptote is 0 if the numerator has the smaller degree. But if m equals n, then the horizontal asymptote is going to be the ratio of the coefficients. And that's what we're learning on Monday. Now, if you're watching this any other year but 2020, we may not be learning this on Monday. All right, so it's the ratio. Let me put that down a little bit. Come on, move down. There we go. So it's the ratio of the coefficients. They are the same degree. They're both got an x to the first power. So this one is understood to be a 1. All right, so the horizontal asymptote is y equals -2, and that matches our graph. And actually all we needed was the vertical asymptote. That was enough. All right, so look to the asymptotes. It's the most obvious thing and the easiest to find. Which of the following rational functions share 0 with the graph shown? All right, so we got to find the 0. Sorry, it's a little pixelated. All right, so it doesn't matter that you don't know how to graph things with squares in it yet. You can factor. So long as you can factor, you're looking for whichever one has now it can have other zeros, right? But it has to have that 0. So that's the only 0 for this function. So when we say 0, we mean x-intercept. Right, so the only one that is 0. So 1, 2, 3. This is -3. So we're looking for who has an x-intercept of -3. Now, how do you find the x-intercepts? Now, I haven't, we've been solving ones that where we had something to add. These won't have anything to add. But you'll see right away what happens when you don't have anything to add, what happens to the denominator. But to find the x-intercept, of course, you set the function equal to 0. But watch what happens when we solve and we have nothing to add. So we have 0 equals x minus 3 divided by x plus 4. If I cross multiply, I have 0 times x plus 4. So that's going to happen all the time. So it's going to end up being whatever is a 0, an x-intercept, a 0 of your numerator, that's going to end up being the x-intercept. But I'm going to cross multiply each time, even though I'm going to get 0 over here, just to make sure it's clear. So we have 0 equals x minus 3. All right, so this would be 3 equals x. But we wanted -3, so it's not this one. All right, let's try the next one. All right, so we have 0 equals x squared plus 7x plus 6 divided by x squared plus 2x minus 3. All right, we're going to multiply both sides. Cross multiply, we get 0 times x squared plus 2x minus 3. Squeeze that in. Equals x squared plus 7x plus 6. Well, this is just 0. X squared plus 7x plus 6 multiplies to give you 6, adds to give you 7. It's going to be 6 and 1. So I don't have a whole lot of space to write that part out. So if you're OK, I'm just going to write x squared plus 6. Actually, I'll write x first. The 6 and the 6x just look so nice together. X squared plus x plus 6x plus 6. And the first two are a group and the second two are a group. We'll factor out the x. We've got an x plus 1. We'll factor out the 6. We've got an x plus 1. All right, so we can factor out that repeating x plus 1. We're left with x plus 6. Our solutions here are x equals -1 and x equals -6. I'm not going to take a lot of time on solving. I think you can figure out that's -1 and -6, and it's not -3, so it's not this one. All right. The next one is really easy to solve. All right. So I'll put it here. 0 equals x divided by x plus 3. Again, 0, we cross multiply, I get 0 times x plus 3 equals x. Well, that's just 0 on this side. You kind of see a trend here. When you multiply by 0, you're going to get 0. Well, that's not it either. So if it's not the bottom one, I've written a bad problem. But I think it might be the bottom one. Let's check. All right, so we have 0 equals x squared minus 3x, oops, except one little thing. I did that on one of the other solving ones. I wanted that to be negative. I'm sorry. It was there all along. Come on. 18. Tell me we can look bad. No, it's like, ha, I'm not going to write your 18. Any day now. Well, it's an 18. I'm going to try and solve minus 18. Isn't that weird? There we go. That should be a negative. All right, otherwise we won't be able to factor it. So when I was writing it, I get the middle term, and then I'm like, forget all about the last term. Sorry, that one should have been negative. All right, so we're going to, and that's divided by x squared minus 2x plus 1. So cross multiply, we get 0 times x squared minus 2x plus 1 equals I'm a little too close to that other problem there. Come on. Oh, seriously. We couldn't all come together? Okay. Equals x squared minus 3x minus 18. All right, of course, that's 0. So multiplies to give you negative 18, adds to give you negative 6 is going to be a negative, excuse me, adds to give you negative 8, multiplies to give you negative 18, adds to give you negative 3 is negative 6 and positive 3. So we have x squared minus 6x plus 3x minus 18. And the first two are a group and the second two are a group. I'm just being a little quick on the factoring because we've been doing that for so long. 0 equals x times x minus 6 plus 3. You can pull out the 3 there because they're both divisible by 3, and that would give us x minus 6. We'll factor out that repeating x minus 6, and we're left with, come on. And we're left with, oh, I already wrote that in there, x plus 3. I wrote my parentheses in twice. So x equals 6 and x equals negative 3. There it is. We found x equals negative 3. And this one was the solution. Oh boy, the pen's being slow. I don't have too many more problems left, thankfully. Oh, it may write it twice. There you go. All right, so when you're looking for x-intercepts, you're going to set the equation equal to 0. Just set the function equal to 0 and solve for x. That's how you find the x-intercept no matter what kind of equation you're working with. All right? So this one had a little bit of work because we had to find all these x-intercepts. So be prepared for that one. But this one is so easy. All right? So I went over it a little bit in that one question. What's the equation of the horizontal asymptote? So I'm going to write in here how you find all your horizontal asymptotes. All right, so n is less than m. In other words, numerator has the smaller degree. It really doesn't matter if you call them m or n, but as long as you remember that the numerator has the smaller degree. The horizontal asymptote is y equals 0, unless a value is added in. So for instance, if I have f of x equals 4 over x plus 9, right? The numerator is degree 0. Denominator is degree 1, right? So 0 is less than 1. So the horizontal asymptote is y equals 0. Right? And it doesn't matter if there were x's on it. That could be 4x cubed and the denominator have x to the 4th. So long as the numerator has the smaller degree, the horizontal asymptote is y equals 0. That's because the denominator is growing much faster than the numerator is. Especially in this case, the numerator is just going to be 4 all the time. The denominator is going to get bigger as x gets larger. Right? And when you divide something into more and more pieces, how big are your pieces? Well, they're like nothing, right? And so the denominator goes to, the horizontal asymptote is 0 because the function goes to 0. So as x gets bigger, you've got so many pieces, the denominator is growing so much bigger, your horizontal asymptote is just going to be y equals 0. Now, if I add something in like this, f of x equals 4 divided by x plus 9, and I add plus 3, all right, I added something in. Now the horizontal asymptote would be, I would just add them together, right? So this one was 0, right, because the numerator was smaller. This one was 3, so y equals 3. Right? What if n equals m? They have the same degree. So numerator and denominator, squeeze over here, have the same degree. Right? Well, then the horizontal asymptote is the ratio of the coefficients. Of the leading term. So I have up above, I have something written to the first power. Let's write something to another power. So what if I have g of x equals 5x squared plus 9 divided by x squared plus 3x plus 6. All right? Their numerator is 2. The denominator is 2. They're both 2. Right? They're equal to one another. So it's going to be, the leading term is the squares, right? They have the most power. If you square something, it will grow larger than if you don't square it. Right? So oops, that's understood to be a 1. So it's not 5 over x. It's 5 over 1. Let me rewrite that circle there. I meant to put in a 1 there. There we go. So in this case, the horizontal asymptote is y equals 5. If we added something in, yes, that would also add something more to it. So if I had g of x equals 5x squared plus 9 over x squared plus 3x plus 6, and at the end I tacked on plus 3, well, then my horizontal asymptote would be 5 plus 3. All right. But you don't have to worry about that really so much. We don't see too many of those. And the horizontal asymptote in this case, it's going to be the ratio of the coefficients. So the horizontal asymptote is y equals 2. Right? And that's all there is to it. If the 2 had been in the bottom, it would have been 1/2, by the way. Right? So it's just however the numbers go. All right? And we're going to find the vertical asymptote and horizontal asymptote of this one. And then I'll see you in the next video, the next to last video. All right, so the vertical asymptote, set the denominator equal to 0. All right, now let me unless you can factor and reduce first. Because remember, if we cancel something out, a canceled factor is a whole, not a vertical asymptote. This is a reminder. Canceled factors are wholes, not vertical asymptotes. But in this case, yes, I can factor, but it's not going to help. It's not going to reduce. I have x plus 6 in the denominator. I could technically factor out the 2, but it really doesn't make much of a difference. If you like it that way, you can have it that way, but it doesn't make any difference. The vertical asymptote would therefore be 2x minus 4 equals 0. Add 4 to both sides. So x equals 2 is the equation of the vertical asymptote. Horizontal asymptote, so notice that the numerator is degree 1. The denominator is degree 1, right? Because you've got an x. An x is degree 1 because it's x to the first power. Right? If that helps, I'll do that. All right, so that means that the horizontal asymptote, here we see n equals m. They're the same degree. Horizontal asymptote is the ratio of the coefficients. Right? And that means we're just going to, here this is a 1, so it's 1 over 2. And it's the ratio of the coefficients of the leading term, I should put. The leading term is the one that's the highest degree. Of course, x is a higher degree than is the constants, who are degree 0. So the horizontal asymptote is y equals 1/2. And there we go. All right, so now we've gone over problems like the solving and graphing rational functions. We have one more, and that's remainder theory. All right, see you in the next video. Bye for now.